Welcome to the panel on Security and Artificial Intelligence, SecAI, at the IEEE Services Computing Conference. I am Bhavani Thuraisingham from the University of Texas at Dallas. I will say a few words about this panel and then hand it over to my colleague, Professor Murat, who will be the panel chair. So, the outline, I'll give the motivation. Why do we need such a panel at IEEE Services Computing? And then briefly discuss three aspects that our panelists will be elaborating on. One is artificial intelligence for cybersecurity. The other is security for artificial intelligence. That's an area that is really becoming critical right now. And the third is artificial intelligence causing security privacy violations, which is a topic that has been researched for several years, but now we may have some new aspects to think about. And then we'll introduce the distinguished panelists. So the motivation, why do we want such a panel at IEEE Services Congress? IEEE Services Congress, with its focus on some critical technologies, web services, cloud, big data, and security, as well as many other areas, it is at the heart of security and AI. The Congress brings together outstanding interdisciplinary researchers who are promoting and working on cutting-edge technologies that are critical for designing and developing large-scale systems that integrate both security and AI, because you can have all the wonderful AI techniques and apply security, but if you can't design and develop them using, say, technologies such as cloud and big data management, then these systems are not going to be of practical use. So I believe that IEEE Services Congress is a right venue to focus and promote SecAI, which is becoming one of the critical fields in computing. So just to give you some idea, the first topic that I mentioned, artificial intelligence for cybersecurity, it has been explored for quite a few years. And here you have applying AI for areas like intrusion detection, malware analysis, and so on. But here some of our work is on insider threat detection. So what do we mean by that? There are bad processes or people pretending to be good people or processes and gathering information from the inside. And so what we are doing here is assuming that data is coming in streams. So the concepts are evolving and they are changing very rapidly. So what we do is we divide the streams into chunks and then we gather the information about the chunks and then we develop models. It's not one model, it's an ensemble of models. And so as new chunks come in for the training, some of the models may not be valid because the concepts have changed. So we throw away the bad models and incorporate some good models. So finally, when we are satisfied with an ensemble, then when a new chunk comes in, say K+1, we extract features and do the testing. And then we will know, is it an anomaly or not? So is it an insider who is a bad process or not? And so we use mainly algorithms like support vector machines, both supervised and unsupervised learning. So that's one aspect. The other aspect the panelists will be focusing on, which is a very, very hot topic right now, is securing AI systems, and in particular, adversarial machine learning. So essentially what's happening is that the adversary modifies data to defeat our learning algorithms. So adversary is trying to figure out what we are up to, our models, we are trying to learn the adversaries' models. Each one is trying to thwart the other person's model. So adversarial machine learning is not about concept-driven online learning, but it's adapting to avoid being detected. So that could happen during training time, testing time, and so on. It's sort of gameplay. So here you see that all these red squares are bad instances and the blue circles are good instances, and this is sort of the boundary for support vector machine. So the whole idea for the adversary is to push the bad instances so that it can pretend to be good. Okay, so they do not get caught. So what are we doing? And we are looking at various types of attacks, but again, we cannot have one solution for all the attacks. That's a challenge we are faced with. So we are looking at certain types of attacks, and we are modifying the support vector machine. So if this is the boundary, classification boundary for the support vector machine is dashed lines, we are developing some algorithms based on the type of attack to push this dashed line to the blue line. Okay, so that's the whole challenge for us. So what happens here, the red crosses are bad instances and the green circles are good instances. So you can see that by pushing the line, the boundary, a lot of the attacks will be caught. Right, so we can figure out that these black crosses are indeed attacks and they are not good instances because we have pushed the line. And so some of our panelists are experts in this field and they will speak more to it during their discussions. And another thing I wanted to mention is that, and something that has been explored for several years now, is AI machine learning. It started with data mining causing security and privacy violations because, for example, you can put collections of data together and it was something using machine learning that is highly classified or highly private. So that's where this whole area of privacy preserving data mining, privacy preserving machine learning. So what we have done is that you've got the decision tree and then you add noise, and then you have the modified machine learning process, such as decision trees. And then the final result, we don't want the final result to deviate. So it should be very similar to what we would have gotten, right, if we did not add noise. And so, again, security and privacy exacerbated as progress is made on AI with new machine learning techniques. So that's why we cannot forget about this area. Area, of course, is access control. We've studied access control for operating systems, for databases, and so on. But now we have AI systems much more complex. They could be planning systems, expert systems, learning systems, and so on. And the question is, what are the appropriate access control models? I'm just saying RBAC, ABAC, CBAC, because that's what we talk about. Are these models really relevant for AI systems? And what are the appropriate security policies? Because we may have to integrate several policies because these systems could be carrying out reasoning, machine learning, and so on. And something else the panelists are experts on is the policy-aware data collection, storage, management, and analysis, which is at the heart of policy-aware big data management. How can we take advantage of that for AI systems? So, finally, our distinguished set of panelists. My colleague Murat Kantarcioglu is the panel chair. He will be moderating. And then we've got some very famous people. Professor Elisa Bertino, who really needs no introduction. She is at Purdue University. And we are also honored to have Professor Hiroki Takakura from the National Institute of Informatics in Japan, who has done some very interesting work on security and AI, and of course Ernesto Damiani, Professor Ernesto Damiani, sorry, I forgot to add the title professor, who is from University of Milano, right here in Italy, who has done some very interesting work also on this topic. And I don't want to take too much time to introduce them, because you can read their biographies in the panel write-up, in the conference brochure. And also, if I were to introduce them and talk about the outstanding work that they have done, I think I can take this entire panel. So now I will hand it over to my colleague, Professor Murat Kantarcioglu, who will be chairing the panel. Thank you.
So I will go next, and I will talk about some of our work on the topic and our views. Then I'll pass to other panelists, so this way we don't switch laptops too often. I guess from my point of view, this is normal, and for many, many years there's this big data revolution is coming. And of course, many people think that cybersecurity is a killer app for big data analytics. But of course, I think the issue is that cybersecurity is different, and security is different in a sense. And many of the existing problems, from intrusion detection to malware detection, have this adversarial behavior where adversary adapts being detected. So if you think about other applications of AI, when you apply in biology, for example, you wouldn't see this malicious adaptation and malicious behavior, where when you apply AI models, you may have noise and other things coming into the system, and you need to deal with that. But here you have malicious noise that are detected. So this is a very active area that people are looking into. And of course, if you look at this malicious behavior, there are really many different threat models, and you need to really consider that. One line of attacks is when you develop or train your AI model, there is this poisoning attacks, where the data sets used for building the models could be attacked by the malicious adversary. And also, of course, there is this deployment and test time attacks. And here the idea is attacker can modify an input to the AI model. And this would happen to cause AI models to function or misclassification. For example, over the years, always spammers try to pass spam filters by adding good words, for example, so the words that are less associated with spam. Or you can add, in a network intrusion detection setting, you can add bytes, etc., to cause errors. So this is the example. If you go to an adversarial machine learning event, you will see how many people have seen this example before? Okay, so it's still relevant. So if you go to an adversarial machine learning event, you will see variants of this example. And the way it works is that if you look at this image on the left, a deep neural network correctly classifies what it is. But then if you add some distortion in the background, although image looks like the same thing to the human eye, now the deep learning model, for example, classifies as ostrich. So this is correctly classified. You add some noise in the background, and it's not correctly classified. So this is an example of test time attack, where you modify the instance, even though you don't change from the human point of view the image that much. Now image is classified something different. So you could see this type of attacks against all type of AI and machine learning systems. Bhavani talked about this example, but I would like to iterate one idea about this. This is our own work. And if you think about to build a classifier to separate these good and bad instances, the regular machine learning model would put it somewhere here. This is the boundary that will classify these two instances. But when you think about adversarial attack, when you think the fact that attacker may modify some of the instances, as we have seen before, you may want to change your classification boundary, maybe to something like blue, so that when attacker modifies some of the instances it controls or add noise to the instances, then the attack will be less successful. Of course, the question is, how do you come up with the blue boundary so it becomes like a game theoretical model where you optimize? People are excited with my talk, I guess. So how do you choose the blue line? So it's basically based on the attacker capabilities and the optimization. And we have papers on that. And of course, the other thing is, what about the attribute you use in your machine learning model? Do you want to use all the attributes? And we have a series of work showing that choosing the right features to build your AI models could be an important aspect. So for example, you can try to choose features that are very highly predictive, but in practice, those features may be modified by the attacker, and therefore, attacker can modify them. So what we have shown is that if you look at these three features, assume you have x1, x2, x3, these M1 means they are normally distributed. If you know that this distribution, this one is very well separated on the feature tree because the mean is 1, here mean is 4. So if you look at basic statistical test, if you just look at one feature to choose, the third one will be the best because it has the nicely separated two classes. This pi1 and pi2 are two different classes. And of course, this one has closer in two classes. So among the three, the third feature is the best feature to choose. This penalty shows how easy for feature to modify. And using game theoretical model, you can show that actually you need really a combination of predictiveness and hard to modify. So in a sense, you need to also consider how attacker can manipulate the feature. And in this case, if you look at this equilibrium, in other words, after an attack, the second one turned out to be an optimal combination of predictiveness, so it's not as predictive as X3, but it is harder to modify compared to the first one, which is very hard to modify but not predictive. So in a sense, you have to really choose your features carefully. So one positive thing is that adversarial attacks are good for privacy. For example, you can see lots of papers out there and work out there that claim that, using ML, we can predict whatever about you, like your sexual orientation, your political affiliation. For example, you can see papers like, if you like curly fries, you are more likely to be high IQ. I don't know how they come up with it. That's just some data mining algorithm. And apparently, if you like In-N-Out burger, you are likely to have less friends. I don't know why. But these are all coming up from mining some data out there. The good news about adversarial aspects is that you can attack these models. So here I have just one slide showing that we attack different type of models. I will just mention one of this. This is a random forest model, and we wanted to attack the sexual orientation prediction. So if we change some of the likes we have on our Facebook profile, we can make machine learning algorithm to classify as any sexual orientation we choose. Furthermore, we have done this type of attacks to look smarter to machine learning algorithms. So if you want to look smarter, for example, you can modify your Facebook likes. So now the machine learning model thinks you are apparently high IQ. It may help, for example, I guess, with job applications. So the good aspect of this attackability of AI models is that you may use it to increase privacy, especially when AI models are used to predict sensitive information. So I guess to summarize, we need to really understand the attacker better, because if we know what attacker can modify and the features it can modify and the cost of that, we could build more robust models. And here I believe game theory, I'm biased, of course, we have done lots of work on applied game theory in this setting, is a natural tool to modify. And at least on the flip side, we can use attacks against ML models to protect privacy. So in other words, at least there is a good aspect that the AI models could be attacked. So I will stop here and pass to Ernesto, and he will give an overview. Please switch to the other laptop.
Also, there should be the remote here. Yeah. Okay, wonderful. So if you could switch to the presentations. Thank you very much. Okay, so just first of all, as you've been told, I'm the local guy. This is our lab here in Milan. Mostly, I will try to go through this very fast, this introductory part. Mostly, in this lab in Milan, we deal with large-scale projects, mostly funded by the European Commission. You see up there one that I would like to mention very briefly, because it also puts together myself and some colleagues who are sitting in the first row here, Ellen and Barbara from the University of Insubria. We are all together in Concordia. This is one of the large 4 pilots on cybersecurity that have been funded by the European Commission. So very quickly, I would just mention this one, specifically because one of the objectives is to improve the understanding and the awareness. And the understanding is basically going to be achieved also by automatic analysis of the data. And specifically here in Italy, we are trying to put together an initiative on basically data analytics for security. And I will try now to sort of give you an idea why I think this is well, related, although not exactly the same thing as AI for security. So let me skip all this. Concordia is trying to achieve a lot of things, but today is relevant because we are going to work specifically on the data analytics part within hopefully, on a number of use cases that will be provided by all the countries represented in the big consortium that's behind this initiative. Okay, so blah, blah, blah. Please refer to our website. There will be a lot to discover, including, hopefully, data sets. Not now, but in the fullness of time. Okay, so what's the agenda for this very quick introduction? I would like to say a few things about the bridge from the past and the present in security data analytics. Of course, AI is the new kid in the block, but we have been doing data analytics for a long while before that. And I would like to finish with announcing an initiative which is a big award that's going to be, well, actually, we are collecting proposals for it right now, and it is about AI in security, and there's a big award of more than $1 million on it. So I will just use my last 30 seconds to announce that one. Okay, so basically, the reason I would like to make you understand why there is a link between the new type of threats, the APTs, the type of threats that affect the large-scale systems today, and the need for data analytics, and eventually for AI. And basically, it shows you this. This is a sort of a standard type of a slide that shows you that the attacker these days are basically doing, well, a work that may last for months and even years, doing infiltration, putting data collection, and data exfiltration support inside the networks. And of course, what we see is the tip of the iceberg of the incident, where basically the data sets are stolen, but this is not, the rest of the iceberg is continuous interfering with the operation of systems, of large-scale systems, both for stealing data, but also for making them work at a suboptimal point. And you see this type of stuff. On our side, the side of the defenders, of course, we are also been collecting data for a long time, and we are trying to do a lot of things. And also, the problem is that we have a supply which is very complex. You can monitor people, you can monitor systems, you can monitor what is in between. And, well, these slides give you a little bit of an idea how complex is the data collection problem in order to be able to identify the activity of an APT within your system. You need to collect data on all the layers of the protocol stack, from the human behavior down to the IoT devices that you may have connected to your network. So this is the situation. And what was the classical answer of the security practitioner to this? Well, the classical answer, the answer of 10 years ago, sorry for stepping back in time with the 3, but it's important that we reconnect to that. The classical answer were signatures. So what is a signature? Basically, a signature comes in 2 types, the atomic signatures on one side and what is stateful signatures on the other. Basically, in a signature is a sort of a pattern that you use to try to recognize an attack. From the point of view of AI people, it's a sort of a statistical regularity of some sort that you're trying to extract from a complex system. But I will comment on this in a couple of slides. So, the easiest type of signature is just an event. You look for an event, and if the event is there, you are sort of suspicious. You go suspicious. The problem is when you are looking for multiple events, because those events can be separated by time. And if you don't know how long will come from one event to the signatures to another, you will need, for example, to allocate a lot of memory just to remember what happened in the past in order to be able to identify the sequence of events that compose the signature. So I will try to, atomic signatures, we teach them to first-year students these days, right? So check whether there is a packet with the SYN bit on without another one previously with SYN and ACK. So basically all these type of things are basically the atomic signatures we look for in the network traffic or in the human behavior. I don't want to bore you with examples. There are many host-based, network-based that you can use. And more or less today, this is part of the standard, let's say, education in information security. The stateful signatures are the ones which basically go from the single event or the sequence of events to a pattern. It's like putting asterisks in an atomic signature. You say that something happens, then something else can happen. You keep on waiting until you see something else coming up. And this is basically a stateful signature. The problem is that, as I said, if you don't know, and the attacker will make sure that you don't know, will randomize the intervals between the event of the stateful signature, pattern matching will not be easy to use, because the attacker will try to make it difficult for a pattern matching stateful signature to be recognized in the network traffic. I hope I gave you the idea. There are many randomization strategies that attackers use to make it difficult to use matching algorithms to find the stateful signatures inside network traffic. And this is something that has been known for a long time, but we didn't really have a countermeasure to that. Okay, so you see slow attacks are the attacks where the attacker has plenty of time, and he will try to sort of fool you by introducing randomization so that the classical pattern matching will not work. Now, let me skip a couple of examples. So this is the situation where AI can step in. AI can step in because AI can provide a way to understand statistical regularities without using standard pattern matching that will require unlimited horizon and unlimited memory, because the AI model can generalize. So basically, it may sort of be capable of detecting a suspicious situation from statistical regularities in the data set that you are feeding. It's easier said than done, though. So this is the reason why everybody is looking at, but there are many challenges. And having worked in practice, and I have some people in the front row that basically are also working in practice on this stuff, these are problems. So fancy models are fine, but these problems, the data collection of data at multiple stacks of the protocols simultaneously in order to be able to apply, to feed the models is not easy, especially in real sites in production. Can be easy in a lab, not really easy in production site. And also they want real time. They want us to detect the attack while it's going on. They don't want post-mortem analysis. And this makes the thing even more difficult to set up. Feeding the models with the real-time data streams is not that easy. Okay, so machine learning, I think, is the answer, yes, but it's not like this to apply. So we are looking at the techniques by which we can make machine learning effective in analyzing multi-layer data, real-time, huge data streams. This is not something that we can easily do today, but we are trying. And my personal view now, 1 second more, it's not going to put all the stuff on the side. It's going to be complementary. So we are not going to kick out single event detection in order to use a sophisticatedly trained AI model, because it is a bad way to use a sophisticated trained AI model to make him detect a single event. So there will be machine learning-based analysis on one side, and there will be the upgrade of the traditional techniques using simpler analytics. Even a regression can do the job for certain type of stuff, and the things will go side by side. I don't see a substitution personally. I see a complementary type of thing. And this is the main message, because again, I didn't want to scratch the surface, but Murat did it very nicely. Transfer learning is a big problem that we have. I can tell you that in the Middle East, the trained systems on network traffic trained in the US require adaptation, require calibration, require additional, the transfer learning problem must be. So the machine learning-based analysis must be focused where it can provide value. You don't want to face the transfer learning just because the average time, installation time of the network support in your Linux platform is different in the US than the Middle East. You don't want to waste training and transfer learning time for that. You want to be able to recognize statistical irregularities that are more difficult. Okay, so now I had a nice example, but it gives me 30 seconds more. Okay, the nice example, just to tell you, we're working a lot on exfiltration techniques because we're working on exfiltration technique is where someone with a probe is using a legitimate protocol from inside to outside to transfer data. And DNS is normally the usual culprit for that. Now, if you would have to train an artificial intelligence model to detect suspicious DNS traffic, so connection to the DNS look normal, they are normal translations, but in reality they are pushing out some bytes each time. So in a month they are pushing out an archive with a very, I don't know, a very sort of a critical data set. How would you do it? What are the features? And I'm connecting again to what Murat said before. Do you want to learn this feature from the traffic? You will become dependent on the specific environment, of course. Or do you want to know in advance and to study in advance which features? We are using entropy of connections, and I'm ready to discuss this offline. And this is a real example with some exfiltration probes that basically from inside the network go outside, and the feature that the analytic model uses are all linked to the entropy of the time entropy of the traffic. Now, let me finish. I want to mention the award. Okay, so with the second hat, I am also running a research center in the United Arab Emirates. This is at Khalifa University and also at the EBTIC Innovation Center, used to be the British Telecom and Etisalat Innovation Center. Together with Dark Matter, we are launching a competition where basically we will cover the academic side. This competition is, you see here, at the end of August, we expect 2 pages proposals. The notion is AI for cybersecurity defense applied to smart city traffic. So we are interested in smart city protocols, and we would want to get proposals, quick proposals by the end of August. Then we will have selection, people will be invited, and very qualified international experts will choose 5 out of those, and then the final winner. It's $1,250,000 for the winner. We may fund 1, we may fund 2 if 2 are exceptionally good. So I would like to finish with this one. Please send if you have ideas on application of AI specifically to the defense of the infrastructures in small cities, well, we are waiting for your proposal. Thank you very much.
So I'll try to be short because we are kind of running out of time. So I will focus mainly on some research directions that I see in using AI, machine learning for cybersecurity based on our own experience. So the first problem that I'd like to, I don't know what happened to my slide. Okay, it's basically the problem that usually when dealing with security and machine learning, you need the training data sets. And usually you don't have a lot of training data sets. And since in security always you have new attacks, new problems, usually you don't have a lot of data set to train your network or your whatever is your machine learning technique. And so that is a real problem. I must say that, for example, there are companies now which even started preparing synthetic data, so at least for research that can be useful. So to address this problem, we decided to really try to apply in practice transfer learning. So transfer learning is a technique by which you train let's say, a neural network on a certain domain, and then you move this neural network to another domain where you have a training data set, which is usually, it doesn't need to be very big, okay? And then we used the same approach in civil engineering, and worked very well. We used the VGG16, we used it to recognize failures in civil engineering infrastructure like corrosion and cracks, and worked very well. And the engineers told me they, for retraining this already trained network, only needed half of the data they would have needed if they had to build a network from scratch. For them, getting the data, labeling them is very expensive. So we used the same for cybersecurity. I'll skip, but we did a lot of experiments, initial ones. We got a very good data set from Australia. And then we tried 2 different networks. And basically, as you can see, transfer learning is much more accurate. We are dealing now with a lot of nice research issues because sometimes when you do transfer learning, you have different features. So you don't have the same features, and therefore you have to do ensemble learning and so forth. But this was very positive and nice, let's say, experience, and we plan to work, trying different types of security attacks and so forth. Related to this, though, there is an interesting problem that basically we are also interested in AI for cybersecurity and edge computing. There are 2 interesting issues. When you do transfer learning, and this was our experience with the civil engineering project, you transfer the network, and again, you need very few data, but the network is huge. So we tried to run it on a small GPU by the company NVIDIA, but the network was too large. So we had to try to do pruning. And actually, the NVIDIA people had worked on pruning neural network, and pruning worked very well because we could cut a lot of portions of the network, and the network was small, accurate, and very fast. But so this is one important aspect. So we plan to do the same for cybersecurity. See now, because the idea would be in the future, you can build this very big pre-trained network, and people can just get them, retrain with few data, and then run them on whatever platform they have, pruning if needed. But for edge is very interesting, and this is actually a project in collaboration with HP. A student of mine did an internship. When you deal with very small devices, sometimes you may want to use an edge server. And so we came up with a nice approach where on the device, you just need to have a trusted log to observe all the events. You transfer everything to the server, which can run sophisticated machine learning techniques, and worked very well. We now plan to extend more that work. The third dimension, the third problem is even more interesting. We are working on cyber-physical system using reinforcement learning. This means that this is a type of, let's say, intelligent system which learned based on experience. It will have a cost function, and will do several experiments and try to optimize this cost function. The problem, though, when you try to apply this where you have safety and security constraint, you cannot just say, oh, the network will learn how not to kill people, okay? Because you cannot allow the network to just do experiments. So the question, it could be good for optimizing energy. No, the device can try various iterations, see when the energy is minimized. So that's a little bit of a problem. So we have been looking into ways of combining a symbolic knowledge with neural network. There is work at CMU where they try to constrain what the network can do based on symbolic knowledge. Symbolic knowledge is knowledge about the domain that you have, which we can constrain what the network can do. So we are still in the early stage of exploration, but this will be an important problem. It goes back to the first keynote, where there was this idea of integrating model-based and, let's say, data-based learning. I believe that this is essential when you have domains where you have safety-critical issues. Because those you cannot afford, again, to have a system that can learn by experience, because in some cases this will involve, again, dangerous situation. continuing with this work, we are also looking at another interesting project where now we want to learn access control policies from data. Elena Ferrari in the past did similar work. Our idea is that today you have so many sources, and we want to learn those policies. The main issue here is that we cannot just deploy a neural network, because policies have to be symbolic, which means you need to give them as input to an access control system. So we came up with an approach in which we combine several techniques. We start with association rule mining, which gives us some rules. Then we augment, because some of those rules can be very low level, so we want to generalize them. We did a lot of experiment, and we noticed in some cases, especially if you use a symbolic learners, we also will be using symbolic learners from logic programming, they can generalize it too much, which for security can be dangerous. So we have to trade off the generality of learning with the security constraint that you have. So basically, we then get this initial set of rules, we generalize them. This is our pipeline. Then we, at the end, we even use a support vector machine, random forest, to add policies. What we realized actually is a very important point, that whenever you have a set of data, if you use a different machine learning techniques, each will give you different knowledge. Because, for example, random forest works more by similarity in a way. Association rules are very precise. So in this way, we have policies which are general, because you obtain policies in the last step, even by using similarity. On the other hand, you can generalize, but not too much, because sometimes you don't want to have a rule like everyone can access this data. This will be too general, may be dangerous. Finally, transfer of policies is also very important. So once you get the policies, also explainability. Somebody may ask you, you have this complicated pipeline, how did you come up with those policies? And once you start having in the middle, let's say, neural network, which we may use as a last step, then you have to explain why the neural network suggested certain rules. So that's all from my side.
Okay, good morning. I'm Hiroki Takakura from National Institute of Informatics from Japan. I'm a director of Center of Cybersecurity Research and Development and NII. So today I want to talk about quite a different aspect of the AI research field. So first of all, our institute operates nationwide academic network. So you can see the from the north to south, and we have United States and Europe and Southeast. We have a huge, very big pipe to the. We provide a big pipe to the universities, but it means we have a big weapon system to the world, because we have a 100 or 200 gig network to the United States. So if the several supercomputers in Japan university are compromised and attacked to the United States, maybe Mr. Trump made such case mad. So we have to protect, we have to prevent such sad stories. Okay, to protect our universities, so we operate the security operation centers, NII SOCs. So we now collect 200,000 hours every day, and we also analyze 900 million session data every day. But we only have a $7 million US budget. So it's so cheap to operate this size of the operating security operation center. So we deployed some machine learning technique to filter out most critical or most dangerous attack among these data. So this is one example. So you can see the April 18th. So we have two huge attacks from actually from France and United States. So our data scientists developed some machine learning technique to identify the criticalness or dangerousness of the cyber attack. So we can see that this day we have two significant cyber attacks to Japanese universities. So I'm a researcher, so I want to investigate what's going on, or why our program detects these kind of activities. However, for our staff, security operator ask us, we should not analyze the reason, because this result shows zero-day attack, because the machine learning techniques reported that something new, something unknown attack were detected. However, signature-based IDS said nothing. So no signature alert, but the significant anomaly. It means it may be a zero-day attack to our universities. So the most important thing to this incident, we have to perform the damage control, not investigate the reason. So most of our operators complain to me, because I'm a director of the center. So why AI system, machine learning system, produces the job to humans? Because AI system, machine learning system can detect something new, something suspicious, or something dangerous activities. Then AI system, machine learning system, order to human beings to fix the problems, but take some countermeasure or damage controls. So they ask our researchers to develop the support system to make damage controls. So, we don't have enough time, because today we have a most important event in the afternoon. So I want to say that. So shall we assign a more intelligent task to AI? Because as I said, AI can provide us the security job, but AI does not provide us some solutions to fix the problems. So we want to develop some solution to support human activities. So traditionally, cyber incident can be taken like this. So we find out some attack or some alert. We just disconnect the machine or network segment from the networks. So it's a very simple and very effective way to protect the cyber attack. However, today, each device interactively work each other. So, and these devices make a very, very complex mechanisms. So nobody knows the exact correlation among devices. So in case of some incident occurred, we cannot identify the impact on our business, or who seems to suffer from the incident. So we need AI try to identify the correlation to analyze the business flow and user informations. And also, we want the AI to estimate the impact of the side effect, because we take some countermeasures, something like we disconnect the machine or disconnect the network segment. It causes a side effect to our business. So we want to AI to tell the side effect of the countermeasure. And also, we want to AI to recommend the best solutions. So, of course, this solution should be make a balance between the effective action to the cyber attack, and also we have a subsequent business continuity planning. So, the right scenario is actually this year's NATO's CCD-CIO, CCD COE's table talk exercise. So you can see the scenario first. Malware infection occurred on the pension system for retired persons. So this is the start point. And the 3 years discussions. So 70 people from all of the NATO people discussed any kind of the mitigations, any kind of countermeasures for 3 years. But almost of them is a misjudgment. Then 3 years later, this exercise fell to the significant crash in energy company stock price. But no one knows. Imagine such a story, because the malware infection causes a side effect to the stock price. But this is an actual story in Japan. Actually, 3 years ago, we have a cyber attack to the pension system, and then our stock price dynamically hold down. So cyber attacks cause many, many side effects, and people cannot imagine such a complicated scenario. So we want to AI system to predict these kinds of scenarios. Okay, I should skip. All right. Okay. And also, we want to make a collaboration to AI, because now AI assigns the people to fix the problem. But next generation, AI and human beings have a collaboration to fix the problems. So, because the AI-only system cannot be feasible in a near future, so we need to make some collaboration between AI and human beings. And of course, AI should support human activities. So we want, our institute want to have something like R2D2 in the Star Wars, not a 3PO. Because we want to the good advisor, good AI advisor to fix the problems. So, thank you.